Okay, so as I was saying in the last segment, limiting reagent or reactant is the reactant that runs out first, essentially. And at that point, you get no more product, so it's called limiting reagent. A reagent is just another word for a chemical or a reactant because it limits the amount of product you can get. We'll also be looking at theoretical yield and percent yield, which are related to limiting reagent. The limiting reagent is the reactant present in the smallest quantities relative to what is required by the stoichiometry and the amounts of the other reactants. Okay, so as I was saying, okay, I wanted to write that out precisely because it's an important definition and it's important to keep in mind when you're trying to determine what the limiting reagent is. It's the substance that's present in the smallest amounts relative to what is required by the stoichiometry of the reaction and the amounts of the other reactants present. It's not just the amount, or it's not just the reactant that you have the smallest amount of. In fact, very often that's not the case. You could have maybe 100 grams of one reactant and 500 grams of the other reactant, and oftentimes it turns out that the one you've got 500 grams of is the limiting reagent. Part of it depends on how big each molecule is. So in other words, for the mass you've got, how many moles is that? And that varies widely from one compound to another because molar masses vary widely from one compound to another. And also, how many moles of the substance do you need according to the balanced equation? You could have a whole lot of moles of the substance, but if you don't have as many as the reaction requires relative to the other reactants, then that's the limiting reagent. Okay, so we'll see some examples of this. So it may sound pretty complicated now, but it's not as bad as it sounds. And again, it's called limiting reagent because it limits the amount of the product that can be made. Now again, using the pizza example, suppose you've got 3 crusts, 27 ounces of sauce, and 17 cups of cheese. How many complete pizzas can I make? Okay. Basically, there are a couple of different ways that you can determine which reactant is the limiting reagent. Doing this question here is basically the easiest of the potential ways. Essentially, you want to take each of the specific amounts of reactants separately, and ignoring the other reactants, and find out how much product you can get from each of those individual reactants. You'll notice that you'll get various amounts of products for the different amounts of the different reactants. Whichever of those amounts is smallest tells you which reactant runs out first, and that will be the limiting reagent. Okay, so from the crusts, we've got 3 crusts, And we know we can get one pizza for every one crust. Notice the crusts cancel, and we get pizzas as a unit for the answer. And note, not surprisingly, that's 3 pizzas. Then from the sauce, the 27 ounces of sauce, we have 27 ounces of sauce, and we can get one pizza according to the balanced equation from every 5 ounces of sauce. Okay, so ounces of sauce cancel as a unit, and you get pizzas as the unit for the answer. And we get 5.4 pizzas from the amount of sauce, ignoring the other reactants. From the 17 cups of cheese, we got 17 cups of cheese. There's one pizza possible for every, what was it, 5 cups of cheese? No, 2. Sorry, 2 cups of cheese. And notice the cups of cheese cancel out, leaving you with pizzas as the unit. 17 divided by 2 would be 8.5. So what we find here from this series of calculations is we have enough crusts for 3 pizzas. We have enough sauce for 5.4 pizzas. And we have enough cheese for 8.5 pizzas. And crusts are the limiting reagent because crusts run out first. Okay, so the crusts run out first. That determines the amount of product we are able to get, and that means crusts are the limiting reagent. Okay, and so again, the crusts are the limiting reagent because they run out after only 3 pizzas. That's before any of the other reactants run out. And you can't get any more pizzas after that. Can't have a pizza without a crust. So that's the end of it. So that's why we say that crusts in this case are the limiting reagent. This is actually the best way to determine which reactant in a situation is the limiting reagent, because in a question like this, the next question is usually going to be, what is the theoretical yield of the product? And the theoretical yield is the amount of product you obtain based on the amount of limiting reagent that's present. So if you were doing the reaction, basically finding the limiting reagent the way I suggested, you would have the theoretical yield already there, and you don't have to do anything else. Okay, so it's the amount of product obtained based on the amount of limiting reagent present, assuming that the reaction goes as planned. Sometimes the reaction doesn't go as planned. Sometimes there are side reactions. Sometimes some of the product gets lost somehow during purification processes or something like that. So you don't always end up with 100% yield. Believe me, you don't. Okay, so the crusts are the limiting reagent, and so above we have the crusts are the limiting reagent. So the other reactants would be known as excess reagents. Things that are present in excess. So in other words, there's some of them left over once the limiting reagent runs out. And 3 pizzas would be the theoretical yield. Okay, so it's not terribly difficult. Because you often don't get as much product as you expect, as I was saying a moment ago, sometimes there are side reactions and you form other products that you didn't expect, or some of the limiting reagent doesn't react for whatever reason, or some of the product can get lost in purification processes and things like that. You don't always get out the theoretical yield. In most cases in real life, you'll get something less than the theoretical yield. And so there is a concept known as the percent yield, which is the actual or experimental yield of a product over the theoretical yield times 100. So if you're expecting 100 grams of product from the reaction and you only get 90 grams, that would be 90 over 100 times 100, or a 90% yield. So just hypothetically, suppose you're making the 3 pizzas, but while your back is turned, your dog eats one of them, and so it doesn't get counted. What would your percent yield be in that case? So what is the percent yield of the pizzas that you actually end up with? So that's going to be the actual yield divided by the theoretical yield times 100, or 2 pizzas, which would be the actual yield, over 3 pizzas, which is the theoretical yield, times 100, which is 67%. In lecture type problems, and we'll do a chemistry example in just a moment, but in lecture type problems, students often get confused as to which number is the theoretical yield and which number is the actual yield, because I don't tell you explicitly. I mean, I'll give you the information, but don't tell you explicitly which is which. But it's not that hard to remember if you think about it like this. Actual yield or experimental yield is the yield that you will get from actually doing the experiment. If this is a lecture question that you're answering on a test or a quiz, you didn't actually do the experiment. And so the only way you would have of knowing what the actual yield is if I tell you. And so the actual yield is the yield that I tell you, and the theoretical yield is the one that you have to calculate. Theory and calculations, we often associate those in our minds. So actual is given to you because you didn't actually do the experiment. Theoretical would be one you have to calculate. And indeed above. 2 pizzas is what we actually had on the counter after the dog ate one of them. And 3 pizzas is what we calculated we should have gotten according to the number of crusts we had. Okay, so it's just actual over theoretical times 100. For a chemistry example, sort of an all-out example that shows all of these concepts, going back to the combustion of octane, we have our balanced chemical reaction for the combustion of octane. I'm going to do this in terms of moles just to make it a little mathematically less elaborate. Normally, you'd be using grams here, so you'd have to change the moles before you could change the moles of anything else. So if we have 10 moles of octane, and it's burned in the presence of 150 moles of oxygen, and 7.25 moles of carbon dioxide are collected, what is the percent yield of CO2? Now, one thing you'll notice in this question is I didn't say anything about limiting reagent or theoretical yield, but you have to find both of those in order to find percent yield. And so sometimes questions are worded like that, and they kind of leave out intermediate steps that you have to do in order to get to the final answer. Okay, so the first thing you have to do is find the limiting reagent. And for that, again, I think it's best just to take the amounts of the reactants and find out how much product you can get from each of them by itself, ignoring any other reactants. And now in this case, we've got 10 moles of octane and 150 moles of O2. You might be tempted just to say, well, we've got fewer moles of octane, so that must be the limiting reagent. But remember, you can't do that because it depends on how much you have relative to how much you need. Notice in the equation, you need a lot more oxygen than you do octane. 25 moles versus only 2 moles. So you can't, just because you have less octane in terms of number of moles, you can't assume that that's the limiting reagent. You have to go in and find out if that's actually true. Okay, so we got 10 moles of octane. And the equation tells us that we get 16 moles of CO2 out for every 2 moles of octane in. Notice moles of octane cancel. And 10 times 16 divided by 2 is 80 moles of CO2 from the amount of octane we have. On the other hand, we have 150 moles of O2, and we get out 16 moles of CO2 for every 25 moles of O2. Notice moles of O2 cancel. 150 times 16 divided by 25 is 96. So we have enough octane to make 80 moles of CO2. We have enough oxygen to make 96 moles of CO2. 80 is less than 96. And so octane is indeed the limiting reagent. And the theoretical yield of CO2 is 80 moles. percent yield is, again, actual over theoretical. Times 100. The actual yield was given back in the problem, 7.25 moles. Is that right? 72, sorry, misplaced that decimal point. Yeah, that would be a really small yield. 72.5 moles of CO2 was collected. And we expected 80 moles. And that ends up being 90%. Wait a minute, it was 72.5. So that's going to be actually a little more than 90%. Let me try that again. 72.5 divided by 80, 90.6. So I would call that, oh, we can use 3 significant figures. So 90.6% yield. Okay, so that's the overview of how you do that. Next, we can do the same, but using masses. Okay, so using that same combustion reaction, everybody's going to have that equation memorized by the end of the session. Using masses, if 100 grams of octane is burned in the presence of 500 grams of O2, and 285 grams of CO2 is collected, what is the percent yield of CO2? And again, in order to find percent yield, you first have to find the limiting reagent and the theoretical yield. Okay, so we have 100 grams of octane. And the atomic or molecular mass, or molar mass, sorry, of octane is 114 grams. And so that means that we have, oh, interesting. I went, oh yeah, okay. So you can keep going to find grams of CO2. We get, okay, so at this point we should have moles of octane, and then we can use the coefficients from the equation to convert to moles of CO2. So moles of octane should cancel now. And then we can use the molar mass of CO2 to convert to, whoops, grams of CO2. And then if you take 100 times, or divided by 114 times 16 divided by 2 times 44, you will have 309 grams of CO2 based on the octane. But there's also the oxygen. Okay, so we have 500 grams of oxygen. the molar mass of O2 is 32. That's, twice the number in the periodic table because oxygen is a diatomic element, meaning it comes in pairs. And at this point, we would have moles of O2. And the equation tells us that we produce 16 moles of CO2 for every 25 moles of O2 that go in. So at this point, we have moles of CO2. And each of those moles of CO2 has a mass of 44 grams. And so now we have grams of CO2. And if you multiply all that out, we get 440 grams of CO2. Obviously, 309 grams is smaller, so that is the theoretical yield. And the limiting reagent is the reactant that leads to the smaller amount of product, and that is the octane. And so there's your theoretical yield, and there is your limiting reagent. And the percent yield is just going to be the actual yield over the theoretical yield times 100. The actual yield, again, is the one that I have to give you in the problem since you're not actually doing the experiment. So that would be the 285. And the theoretical yield is the one that you calculate, which is the 309 in this case. And 285 divided by 309 times 100 is 92.2%. Okay, so remember, the limiting reagent is not necessarily the reagent that you have the smallest mass of or even the smallest number of moles. It's the one that you have the least of compared to what you need. And in order to find that out, you really need to go through the calculations and find out how much product you can get from each of the reactants. And whichever one produces less reactant, there's your limiting reagent. Okay, so as one more example. There are several different ways to make ammonia. One of them is to combine the elements involved in ammonia, which are hydrogen and nitrogen, like so. (3H2 plus N2 yields 2 NH3. NH3 is the formula for ammonia. Okay, so what is the theoretical yield of ammonia in kilograms possible from 5.22 kilograms hydrogen and 31.5 kilograms nitrogen? Okay, so we have to find the limiting reagent. The only curveball for this question is that the masses have all been given in kilograms. but we can easily change those to grams by multiplying by 1,000. So for the hydrogen, 5.22 kilograms times 1,000 grams per kilogram gives you 5,220 grams of hydrogen. And hydrogen as an element, remember, is diatomic. So there are 2 grams of hydrogen per mole. And the equation, at this point you would have moles of hydrogen. The equation tells us that you get 2 moles of ammonia out for every 3 moles of hydrogen. And, there are 17 grams of ammonia for every mole of ammonia. And so 5220 divided by 2 times 2 divided by 3 times 17 gives us 29,580 grams of NH3. Okay, from the amount of hydrogen we have, or from the nitrogen, there's 1 mole, 31.5 kilograms times 1,000 grams per kilogram means we got 31,500 grams of nitrogen. And remember, nitrogen as an element is also diatomic. And so there are 28 grams of nitrogen per mole, twice the number in the periodic table. The equation tells us that we get 2 moles of NH3 for every 1 mole of N2, and there are 17 grams of NH3 per mole of NH3. Okay, 31,500 divided by 28 times 2 times 17 gives us 38,250 grams of NH3 based on the ammonia. Of those 2 numbers, clearly the first one is smaller, the 29,580. And so that is our theoretical yield. And the limiting reagent is hydrogen. And the theoretical yield is 29,580 grams. You would divide by 1,000 to put it back in kilograms. So 29.58 kilograms. Or 29.6 actually, in 3 significant figures. And so that would be your theoretical yield. Okay, I'll do one more example here. Reduction of iron ore to iron metal is an interesting reaction. Iron ore mostly takes the form of iron 3 oxide, which is rust, essentially. Iron ore is kind of orangey red, which is basically rust. And you react it with carbon monoxide, and you get iron metal and carbon dioxide out. And so that's actually a fairly easy reaction to carry on. So if you react 167 grams of the iron 3 oxide with 85.8 grams of carbon monoxide, and you get 72.3 grams of iron, what are the limiting reagent, theoretical yield, and percent yield? I'm just going to say what is the percent yield because, of course, you have to find all that other stuff before you can find percent yield anyway. Okay, so first thing you want to do, again, is find the limiting reagent. Take the two reactants separately and find out how much product you can get from them, ignoring the other reactant. Yeah. 167 grams of the iron oxide. We need to know the molar mass. So if you go to the periodic table, take 2 times the mass of iron and 3 times the mass of oxygen, you get 160 grams of iron oxide per mole. Whoops. Grams of iron oxide cancel, and you end up with moles of iron oxide at this point. You can then use the stoichiometry of the equation to transfer or transform that into moles of iron. Again, what you're going to on top and what you're coming from on the bottom. You get 2 moles of iron out for every 1 mole of iron oxide going in. Moles of iron oxide now cancel, and we're over to moles of iron. Now we can use the molar mass of iron from the periodic table to find out the mass of iron. And it is, I'm going to round it off to 56 grams of iron for every mole of iron. The masses we're being given here in the problem aren't really accurate enough to justify using all of the decimal places in the periodic table, molar masses. So I'll round that 55.85. I'll just round that off to 56. And let's see, moles of iron cancel out. You get grams of iron as your unit. And when you multiply all that through, it results in 116.9 grams of iron. So you have enough iron oxide to make 116.9 grams of iron. But how much of the carbon monoxide do you have? You get 85.8 grams of carbon monoxide. According to the periodic table, there's 28 grams of carbon monoxide for every mole of carbon monoxide. This would give you moles of carbon monoxide as a unit. The equation says we get 2 moles of iron out for every 3 moles of carbon monoxide in. So now we are over to moles of iron, and then 56 grams for every mole of iron. And therefore, we have enough carbon monoxide to make only 114.1 grams of iron. And so that is going to be your theoretical yield. And the limiting reagent is carbon monoxide in this case. In real life, the limiting reagent would normally be the iron oxide. Okay, and the percent yield would be the actual yield or the theoretical yield times 100 Again, the actual yield is the one that you're told in the equation, which is 72.3 here. And the one you calculated is the theoretical yield. 72.3 over 114.1 is 63.2% yield. Actually, not very good. But, oh well. These things happen. All right, so that's a pretty good overview of theoretical yield and percent yield, stuff like that. That's also the end for this segment of the lecture, but we'll be back with part C in a moment.